All right, here we go with the Chapter 5 Homework A review. So this will be the first of two assignments that deal with Chapter 5, where we started talking about moles and stoichiometry and all those fun topics. The class average this week was 9.42 out of 12, which is basically identical to last year's average. So we did okay on this one. I think what you'll find with this homework, starting with this assignment and for the next several that we'll have, is that we're getting into a part of the course where we're going to be mostly dealing with numerical questions, not nearly as many conceptual. And while it's not necessarily more difficult, I would say, I think for most students are actually more comfortable with these types of problems. The issue is that for a lot of the questions, you have to do multiple steps and then enter in a numerical answer. And if you just mess up one of the steps, you get the whole problem wrong. So it's very possible in this part of the course to know 90% of the material and still miss a lot of questions because of that little bit you're missing. So it is very important to be, very detail oriented, do a lot of practice, and certainly, give some assistance on any problems that you might have got wrong. Because a lot of times it's just one little thing you're missing. It's not usually a huge issue. So I'll go through several different problem types. These are all ones that I identified in Blackboard as the ones that we had trouble with. And then, as usual, if you have additional questions on the homework assignment, please come see me in my office hours. All right, so the first question, there were actually several of this type, this general variety that we had trouble with. And what actually turned out to be the case is that this was not even a question that really dealt all that directly with the new material in Chapter 5. This was something way back from Chapter 1 that we learned. So I think for a lot of people, we just probably tried to make this more difficult than it was, or perhaps have not retained things from that long ago in the course. But this is just dealing with mass percents and mass ratio. So here if we have a mineral contains only a metal and fluorine, so just two elements. If analysis indicates that a sample of the mineral contains 175 grams of M and 101 grams of F, what mass of fluorine is present in 123 grams of the mineral? So in this problem, we're not going to use any relationships involving moles. For one thing, we don't even know what the identity of M is, so we can't really convert the masses into moles even if we wanted to. But as it turns out, we don't need to do that anyway, so there's a much simpler way to handle this. So what we'll start with is the information that we're given in the problem is that a sample of the mineral contains 179 grams of metal and 101 grams of fluorine. And because of conservation of mass, if these are the two masses of the elements, those would combine to make 280, if I did my math right, 280 grams of the mineral. Whatever the formula that is not given exactly. Okay, so this is our given information, and as you'll recall from what we learned early on in the course, we can make ratios out of any of these masses. So 179 grams of metal per 280 grams of mineral, 101 grams of fluorine per 280 grams of mineral, 101 grams of fluorine per 179 grams of metal. Any of those can be written as a ratio that we can use to convert between amounts of substances. So then what we want to find, and this is what's given in the second half of this question, what mass of fluorine is present in 123 grams of the mineral. So what we're looking for is basically the mass of fluorine, and what we're starting with is 123 grams of the mineral. Okay, and then what we can do, as I said, is write ratios of any of these amounts. And so what we want is we want grams of mineral to cancel, and we want to convert that into grams of fluorine. And we can do this in one step by using these given numbers. Now, we could convert these numbers into simpler ratios or percentages, but we could just use the raw numbers too, which is what I'm going to do here. So what we find from the given information is that there's 101 grams of fluorine per 280 grams of the mineral. And so that allows us to convert and figure out how many grams of fluorine are in 123 grams. And so we just have to multiply this and divide. And what we should get, following the rules of significant figures, is 44.4 grams of fluorine. Okay? So this was a problem that had variable numbers. So the numbers that you might have had were likely different, almost certainly different than this. But at the same time, it's going to be the same set of steps. And we can just use mass ratios of elements directly. We don't have to do anything with moles in this problem. And there were several problems like this on this assignment that were actually some of the ones we did worse in, and I think it's probably just because we tried to make them harder than they were. All right, but the rest of these do deal with some of the new topics we've learned. And so one of the first things we talked about in this chapter was molar mass, basically for an element, the molar mass is just the atomic mass, what you get from the periodic table. For a compound, it's the sum of the atomic masses, and that's what we're doing here. What is the molecular or formula mass of a compound with this formula? So again, generic formula with some elements that aren't real elements, M and X. But here we're told that the atomic mass of M is 105 and that of X is 36. So we just want to find the atomic mass from this. All right, so what we need to do is, if we're going to find the molar mass, it's just going to be the sum of the atomic masses. So we have the metal M, we have 3 of them in the formula, so it's going to be 3 times the atomic mass of M, which is 105 AMU. And then we have X. Now we have to recall that we have XO4 taken 4 times. That means we're going to have, basically in the formula, 4 XO4s. We want to write them out individually. And so that means we have a total of 4 X's. We distribute inside the parentheses. There's 4 X's in the formula, and the atomic mass of X is 36. And then the last thing we have to do is oxygen. So each XO4 anion contains 4 oxygens, and there's a total of 4 of those in the formula, so that's a total of 16. Or as I showed over here, 4 plus 4 plus 4 plus 4. So we have 16 oxygens. We need to find the atomic mass of oxygen. And so for that, we're going to go to the periodic table because oxygen is a real element, so we can find it in the periodic table, and we need that number to do this problem. All right, so if we find oxygen, we've used this number a lot in class, so it should start becoming familiar without even looking it up. Oxygen is here, 15.999, 16.00 is close enough. And so that's what we're going to put in for oxygen. So there's 16 oxygens, each has a mass of 16 AMUs. And so we're just going to add these 3 together. 3 times 105 plus 4 times 36 plus 16 times 16. That's the masses of all the elements, accounting for how many of each of those elements is in the formula. And so when we do that, let me work out the math real quick. It's a large number. When it comes out to 715 AMU. And as typical, we would just enter this in as a number. All right, so that should be correct for that one. Just calculating the molar mass. In this case, we didn't have real elements, but it works out the same. All right, so that takes care of that one. We did, I think for the most part, we did fine with determining molar mass. Just this one, for whatever reason, tripped us up a little bit. All right, and then the next 3 problems are all somewhat related to each other, and they're dealing with mole relationships, in particular mole relationships involving Avogadro's number. So if you'll recall, the definition of a mole is 1 mole. It's a counting number, and it's 6.022 times 10 to the 23rd. There's a lot of different ways of saying this, but I guess entities is perhaps the most technical way. But the key point is that if we have a mole of a substance, there's going to be 6.022 times 10 to the 23rd of whatever fundamental particle makes up that substance. So if we have an element that's just an atomic element like a metal, for example, sodium, 1 mole would contain 6.022 times 10 to the 23rd atoms. But if we're dealing with a compound, like in this case water, 1 mole would be 6.022 times 10 to the 23rd molecules of water, because water is made up of H2O molecules. And so we have to make sure we keep in mind that when we're using Avogadro's number, which type of atom, molecule, particle, whatever, does this number represent? So that's where writing it out is helpful. So in this case, we just want to know how many molecules are contained in 9.83 moles of water. And so this ends up being a fairly simple conversion. So we're looking for the number of water molecules. So we're going to write out what we're looking for, and what we're told is that we have 9.83 moles of H2O. And if we want to go from moles to number of molecules, water is made up of molecules, so all we have to do is just a simple conversion using Avogadro's number. So we want moles to cancel out, and we want to find how many water molecules there are, and that's just going to be Avogadro's number, 6.022 times 10 to the 23rd water molecules in 1 mole of water. Moles cancel out, and so this particular problem was just a simple 1-step conversion. And so what we get is 5.92 times 10 to the 24th water molecules. Now, as is typical, especially in homework questions, which we're designed a long time ago. What we want you to do in this case is determine the log of the answer. So the log of this number, so make sure you know how to do logs on your calculator, because we're still going to have it to some extent in this part of the course. When we take the log of that, we get 24, and they want 3 decimal places, so it'll be 772 would be the way that we would enter this into Blackboard. All right, again, no real reason to take the log of this number. It's just that it's a more convenient way of entering the number into Blackboard instead of dealing with scientific notation. All right, but this problem was just one step because we have moles of water. We want to know just how many molecules there are, and so it's just multiplying by Avogadro's number. Now the next two are much more commonly missed problems, and that's because there's one additional step that we didn't really talk about directly in class, and a lot of students miss, especially the first time they're dealing with it. So in this case, we want to know how many moles of hydrogen atoms are present in 1.72 times 10 to the 24th molecules of CH4. So in this case, we're sort of going in the opposite direction. We want to know how many moles of hydrogen there are, and we're starting with 1.72 times 10 to the 24th CH4 molecules, methane. Okay, so that's what we're starting with. Now I think what a lot of people did here is they did the first step correctly, but then they just stopped after this first step. So you have number of molecules, you want to get into moles, so of course your first thought should be Avogadro's number. So a lot of people just divide it by Avogadro's number to get molecules to cancel out. But the problem is we can't stop here, because as you'll recall, CH4 is a covalent compound with the formula CH4, and that means when we convert to moles, this is going to be moles of CH4 when we divide by Avogadro's number. So if we have this many molecules of CH4 and we divide by Avogadro's number, that's going to tell us how many moles of CH4 we have. But what we're looking for here is moles of hydrogen, so we can't stop at this step because this is just moles of CH4, not moles of hydrogen. And so the last step we need to do is recall that in a chemical formula, the subscripts after each element tell you how many moles of that element are in 1 mole of the compound. So if we have 1 mole of CH4, the formula tells us that there's 1 mole of carbon and 4 moles of hydrogen. So if we want to go from moles of CH4 to moles of hydrogen, we need to use the subscripts in the chemical formula. So there's 4 moles of hydrogen per mole of CH4 because of the subscript 4. And so this last step here, multiplying by 4, was the one that I suspect most people missed when they did this problem. And again, I think this might have been a problem where the numbers could have been variables. So you might not get the exact same numbers here, but the same steps would be needed to solve the problem. So we're going to divide by Avogadro's number to get moles of CH4, but then we have to quadruple that number to get the number of moles of hydrogen atoms. What we get, reporting to the correct number of decimal places, is 11.42 moles of hydrogen. And if this, and then I guess as the problem suggests here, we would just enter in the number. Come on, 11.42. Okay. So that's a step that people forget a lot, because when you're dealing with Avogadro's number, that's going to tell you the number of things that make up that substance. If that substance is a covalent compound, Avogadro's number would tell you how many molecules are in 1 mole, but they don't tell you how many atoms necessarily are in 1 mole. All right, and then a very similar problem here. This time we're starting with a mass, though. So what we want here is the number of chlorine atoms present in 27.5 grams of chloroform, which has the formula CHCl3. All right, so again, multi-step problem. Let's just start from the beginning and figure out what steps we need to get there. So we're looking for the number of chlorine atoms. So we want to make sure that when we do all these conversions that we get to this quantity here. And what we're starting with is 27.5 grams of CHCl3. All right, so the first step is if we're in mass. Now we know that we're trying to go to number of atoms and we're in mass, so we should probably go through moles. Remember that there's no real direct way to get from mass to number of atoms, but we can get there if we have the moles of the substance. So we're going to first convert to moles. We want moles of CHCl3 in the top and then grams in the bottom to cancel out. And so what we need is we need the molar mass of CHCl3. So what we're going to do is we're going to take the atomic mass of carbon, which is 12.01, plus the atomic mass of hydrogen, which is 1.008, and then 3 times the atomic mass of chlorine, because there's 3 Cl's in the formula, which is 35.45 for each. And what we get is, sorry, hang on a second. All right, so what I got was 119.37 grams per mole. All right, so that's the molar mass of CHCl3, so we're going to put that number in the denominator, 119.37 per 1 mole. So that's going to get us into moles of CHCl3. Now from here we have sort of two choices on how we proceed. We can convert moles into number of molecules, or we can convert moles into moles of chlorine. There's a couple ways of doing this. So the way that I'll do it is I'll just take this and we'll use Avogadro's number to figure out how many molecules of CHCl3 there are. So there's going to be 6.022 times 10 to the 23rd molecules of CHCl3 in 1 mole. So that gets us into number of CHCl3 molecules, but again, we're looking for, in this case, number of chlorine atoms. So we can't stop here. The formula CHCl3 tells us that there are 3 chlorine atoms in 1 molecule of CHCl3. All right, so again, these chemical formulas can be interpreted either at the molecular level. CHCl3 tells us that there's 3 chlorine atoms per molecule, or we could have done it at the molar level and said that 1 mole of CHCl3 contains 3 chlorine atoms. So the order for these last 2 steps, multiplying by Avogadro's number and then multiplying by 3 to account for the number of chlorine atoms in the formula, those could have really gone in either order. So if you did it that way, that's fine. You'll get the same answer, and it's certainly a perfectly valid way of doing it. But these are the steps you need, and this is the step, again, that I think was most commonly forgotten, is because if we want number of chlorine atoms, we need to account for the fact that there's 3 chlorine atoms in each molecule of chloroform. All right, so when we multiply and divide this across, we get 4.16 times 10 to the 23rd chlorine atoms. And again, we want to take the log of this number. So the log of this would be 23, and I guess they want 3 decimal places again, so 23.619. Okay. All right, again, log is just to make Blackboard happy, not for any real reason. All right, so that's how we do this problem. So these last 3 were all related to each other, but in the last 2 that we did, we had to remember that we had to account for the chemical formula and make sure we look closely at what exactly we're looking for and not just stop too early. All right. And then the next, I think there's just a couple questions left. Yeah, just 2 questions left deal with determining chemical formula, or in this case, the unknown element. So I think I left out a word here. This should be by mass. So anyway, what this problem says is that a metal oxide with the formula M2O contains 11.18% oxygen by mass. Type the symbol for the element represented by M in the box below. Now, we have not seen a problem like this, so it's understandable that there might have been some confusion. But we're going to start in this part of the course dealing with moles now. There's going to be sort of a lot of questions that I'll ask us to identify unknown elements. And when you want to identify an unknown element, typically the way we're going to do this is we're going to try to find the atomic mass of the unknown element, okay? And so the 2 things we need to find the atomic mass of an unknown element are going to be the mass of the element, which in this case the unknown is called M. And remember that atomic mass is grams per mole, so we need these 2 quantities. So in a problem like this, we want to find both the mass and the moles of the metal. Dividing the 2 gives us the atomic mass, and then from the periodic table, once we have the atomic mass, we can figure out which element that is that corresponds to that atomic mass. All right, so we need these 2 things. The first thing we're told is that the mass percent of oxygen is 11.18%. So if we assume 100 grams of the oxide, what we know is that we would have, because it's 11.18% oxygen by mass, that means in that 100 grams we'd have 11.18 grams of oxygen, and then the rest of that 100 grams, so we would have, and then the mass of the metal is going to be 100 grams minus 11.18. So it's just two elements in the formula, so the sum of the two has to equal the total. In this case, we're assuming 100. So we have 88.82 grams of metal. Okay, so we have the first part, and so as is typically the case when we're dealing with mass percents, we assume that we have 100 grams of the compound, and then we can interpret the percentages as just mass amounts, because percent means how many grams out of 100 there are. All right, so if we have 88.82 grams of metal in our 100 grams, that's the first part. So that one we didn't really have to do much work to get. But now we figure out how many moles of metal there are in that. And the way we're going to do this is we don't know the identity of the metal. That's what we're trying to find. So we can't find the number of moles starting with the mass of the metal. But what we can do is we can start with the mass of oxygen. So if we want to find how many moles of our unknown metal there are, we know that we have in this sample 11.18 grams of oxygen. And we can find the moles of oxygen because we know what element it is, so we can use its atomic mass. So 1 mole of oxygen has a mass of 16.00 grams. That's the atomic mass of oxygen that we used earlier. And now that we have moles of oxygen, we also know the chemical formula of the compound. And so what this tells us is that M2O, there's 2 moles of metal for every 1 mole of oxygen. And so we can use this ratio, 2 moles of M for every 1 mole of O, which comes straight from the chemical formula. So we couldn't do this without knowing the chemical formula was M2O, but if we know the ratio of the moles in the formula, we can use that to figure out of this 100 grams, how many moles of metal does that correspond to? Sorry, 11.18, we're going to divide that by 16, and then twice that number gives us the moles of the metal, so it's 1.398, I'll keep one extra decimal place just to, I guess that's about the right one. Okay, so 1.398 moles of metal. So we're going to divide this in the denominator here. That's going to be 1.398 moles. All right. So what we found using mass percents and then now mole conversions is that there's in 100 grams of sample 88.82 grams of the M and 1.398 moles, and then dividing the two will give us the molar mass of M. So that gives us 63.11, and what we need to do now is go to the periodic table and figure out which atomic mass is closest to that. So if we go to our periodic table, we want to find a atomic mass of 63.11, and the one that's closest is going to be copper. Now, I don't know if I messed up my math somewhere because it should be maybe a little bit closer than that, but anyway, copper is clearly the one that's closest, 63.11 grams per mole. And so that means the metal in this case is going to be copper because that's the element that has the atomic mass closest to that. All right, I double checked my math, didn't do anything wrong, so it doesn't work out perfectly because we got 63.11 and the atomic mass of copper is 63.55, but it's certainly the closest of all the elements in the periodic table, so that's what we'll go with. So for problems like this, anytime you want to find an unknown element, we'll see a lot of variations on these in the next few chapters. Typically what you're going to do is you're going to find the mass in the moles, divide the two to get the molar mass, or atomic mass in this case, and then identify it from the periodic table using that number. All right, so the last problem is a pretty typical one of using now mass percents to determine empirical and molecular formula. So in this problem, we're told that we have a compound that's just 10.13% carbon, 89.87% chlorine. We want to determine the empirical and molecular formula given that the molar mass is 237. So with this type of problem, there's going to be a few steps involved. The first one to get the empirical formula is we're going to, again, assume 100 grams of compound because we're given mass percents. Anytime we're dealing with percentages, that's going to be sort of the way we go. And then if we're assuming 100 grams of compound, these percentages will tell us how many grams of each element are in that 100 grams. And so the first thing we're going to do is to find the mole ratio of these elements, which will give us the empirical formula. We're going to convert each of those masses into number of moles. So we want to find the moles of carbon. We have 10.13 grams of carbon, and then we're going to use the atomic mass of carbon to convert grams into moles. So 1 mole of carbon has a mass of 12.01 grams. And so what we end up with is 0.8435 moles of carbon. And then the next thing we're going to do is do the same thing for chlorine, moles of Cl. We have 89.87%, so 89.87 grams of chlorine in 100 grams of the sample. And then we're going to use the atomic mass of chlorine. So if we find that in the periodic table, it's 35.45. I think a number we've also used earlier today. And so what we get is 2.535 moles of Cl. So to find the empirical formula, we're going to try to find the smallest ratio of these, convert it into a whole number ratio. And so we have C 0.8435, Cl 2.535, and then we're going to divide both of these numbers by the smaller of the two, which is the 0.8435 for carbon. And so what we get is C1, and then if we divide 2.535 divided by 0.8435, we get Cl 3.005. That's close enough to just say CCl3. All right, so that's the empirical formula, but this wants us to find the molecular formula. And so remember, the way that we're going to do that is we're going to use the molar mass, and we're going to compare that to the empirical mass. So the empirical mass of this compound, because remember that the molecular formula is going to be some whole number multiple of CCl3. So the molecular formula could be CCl3, but it could also be C2Cl6, it could be C3Cl9. Basically any multiple of this formula could be the molecular formula. So we're going to compare the empirical formula to the given molar mass. The empirical mass is going to be 1 carbon and 3 chlorines. And so when we add those up, we don't need to be super precise with this. We get 118.4. And then if we divide the two, the molar mass divided by the empirical mass, the molar mass is given to us as 237. And we just found that the empirical mass is 118.4. And that looks like it's going to be a ratio of 2. It's basically, yeah, it's 2. So what this means is that the molecular formula is 2 times the empirical formula. So that means we're going to take CCl3 and we're going to double the whole thing to get the molecular formula, and we get C2Cl6. All right. So as we talked about in class, when you have mass percentages, you cannot find the molecular formula directly. You can only find the empirical formula. But if you know the molar mass and you compare it to the empirical mass, that will tell you what multiple of the empirical formula is the molecular formula going to be. So in this case, it's a multiple of 2 because the molar mass is double the empirical mass. All right, so that takes me to the end of what I wanted to cover today. In this homework set, it was mostly as problems like this with just a lot of mole conversions involving Avogadro's number and molar mass. In the next chapter 5 assignment, we're going to have a lot with stoichiometry, so those will be some additional steps involving balancing reactions and reaction coefficients and things of that sort. So we'll cover all that in the next review and a little bit more in class today. All right, so I will see you guys in class later this afternoon.